Welcome to the course on two-dimensional signal processing, principles and practices. After doing this 2D DFT and the DCT, we'll also look into this DST, Discrete Sine Transform, and we'll correlate with all of them, DFT, DST and DST, DCT and so on. So first, taking this 2D DFT, how do we consider that linear transformation case of row-wise and column-wise decomposition? So we have done this in the 2D DFT, row-wise and column-wise decomposition, whereas we have taken an X of n 2D sequence in which the first 1D N1 point DFT is computed and getting the intermediate signal. After that, 1D N2 point DFT is computed for each column of that. So this can be done in the other way also. First, we can take the X of N1, N2 column, 1D N2 point DFT, and then make this intermediate signal and compute the row-wise DFT. So for considering the column-wise DFT here first in the composition, that is of column and row column decomposition. So X is written as considering in the matrix form X0, X1, X2 are the samples of up to N2 minus 1. So you can have each column of the X. Okay, and then Fn1 is that N1 cross N1 1D kernel matrix. If you recall that twiddle factor matrix, so this is now talking about the twiddle factor matrix for the 1D DFT computation. So then take this and to compute the intermediate sequence, that is G, which is multiplying this X, each column with this matrix, kernel matrix. The twiddle factor matrix is nothing but the kernel matrix, and get the intermediate sequence. So that would be getting the column, each column. So if you take the column and then 1D DFT, take the 1D DFT of N2 point and get the column of the intermediate sequence, and this column is again taken, each column, and multiplied by the kernel matrix that is corresponding to 1D kernel Fn2, and take the 1D DFT, that is multiplying this kernel with the intermediate sequence and getting that each row. So each row of the Y or the convolved, or the case of computing the 2D DFT of the sequence. So in that B is represented as the 2D DFT of the matrix X, which is given. So that means F, W, X and W, where N1, N2 the transpose is here, that is, can be interchanged. So Fn1 into X into Fn2 transpose. So this way we can say that row column wise decomposition can be done by knowing the X, but just by multiplying the twiddle factor matrices in this fashion to getting the 2D DFT. This order can be changed, but we can get this B. This is the transformed sequence. Now the same thing we can apply to DCT as well. 2D DCT we have seen in the previous lecture, that equation and its basis function. So the coefficients C of K1, K2 for a sequence X is K1 and K2 varying in this range is expressed as like this. So for the inverse DCT, we know that 2D DCT again by having these coefficients we can get back this, where W1 and W2 will take the case of 1 by 2 for K equal to 0, and if K equal to 1, that is 1. So those factors can be used for DCT pair, that is from going from one domain to another domain. So now taking this DCT also in a separable form, like row column wise decomposition, because it is separable, that DFT is separable. We have done row column wise decomposition, and we have applied the separability in various aspects like convolution also we had done, and the impulse response is separable, and we did the 2D analysis with 1D. So if it is separable, DFT is separable, again we had done it for the case of DFT, 2D DFT with row column wise decomposition, either row wise DFT, 1D DFT, and then column wise 1D DFT, or column wise 1D DFT and then take the row wise 1D DFT. Both the ways it could be done. So similarly, considering this 2D DCT in the separable form, so we get X of N1, N2 and consider that as in the matrix form X, and its 2D DCT is that unitary one, similar to the case of DFT, CX C transpose. So this C is now the kernel matrix of DCT. So this kernel matrix comes from the basis function. So we can always take that values. How do we get this? This is real and unitary, and this C matrix is real and unitary here. So we can get the transformed, that is the coefficients of x here, DCT coefficients of x, but by considering x as a matrix, and C transpose C can be obtained from the basis function, and then we multiply them, we can get it and V. So the x, similarly, to get back the sequence C transpose VC, if we multiply in this order, we get back the x. So in matrix form, it's also easier to get in this person. C is unitary and real matrix. So now coming to the discrete sine transform. So we as we considered in this DCT, 1D DCT we had done, and then extended to 2D DCT. So in the case of DST, it is also used for this energy compaction property of this. So let's take this x of n be a sequence of length n, and in which that is valid only for the samples this. And what is the 1D DST of it? So the x of n, can see the sine of pi in k plus 1 n plus 1 by n plus 1, where k is varying from 0 to n1 minus 1. So this is the factor which is the scaling factor used to get this coefficients xk, which is the sine transform, that is discrete sine transform of x. Okay, so this factor is root 2 by n plus 1. We can take this one and consider getting the DST for it, and into inverse DST is that xk, that the coefficients what we had from that the basis function, multiplying it for k is varying from 0 to n minus 1 for summing up these coefficients, and the factor remains the same, 2 by 1 plus 1. So as we have seen that in the DFT also, we have used in the inverse transform that scaling factor, and similarly in the DCT also. In the DST it is used equally, and it is to get x of n and x of k, or the sxk here. So this is inverse DST. So now what is the kernel of the DST? That is the basis function. So this is the basis function, and 2 by n plus 1. So for the given signal length n, so the k is the bin index, as we have discussed in this DFT and DCT. Everywhere this k represents the frequency bin index, and small n is the time domain samples. So we can have this kernel matrix kn 2 cross 2. We can obtain this kernel for the kernel varies from n is varying from 0 to n minus 1, and k is varying from 0 to n minus 1. So if we take it, we will get it as a 2D or the matrix form of kernel here. So this is obtained from the basis function here. And in the matrix form, we can represent that to get the coefficients, multiply this S into the sequence X. That is, this is the kernel matrix, and then X is the 1D case. Here it is n cross 1 input vector. The compatibility needs to be checked. This is n cross n, then this would be n cross 1 for the multiplication. And the Sx is n cross 1 transformed vector. Obviously, if it is n cross n, depends on that this is n cross 1. So we get this n cross 1 Sx, and the transform vector is this. So multiplying this with the kernel, the X sequence with the kernel would result in the transform vector, or the DST taken X is that DST coefficients are this. So the S is n cross n. So now this is having the orthonormal property. The DST matrix is orthonormal, whereas we had seen in the DFT the kernel matrix or the total factor matrix is unitary and orthogonal. So here is that this is DST matrix is orthonormal, and so S inverse is S transpose. So we have, and the real value DST for that S transpose into S equal to this identity matrix. S into S transpose will be the identity matrix. Well, if we take an example of DST, and let's say that 1D DST taking that X is this. That is a 1D sequence, 4, 3, minus 1 and 6, and this represents the 0 when it is not mentioned that the first value is corresponding to the 0. So for this, how do we get this 1D DST? So take the kernels, that is using the basis function 2 by n plus 1 sine pi k plus 1 into n plus 1 by n plus 1. So substitute here k and n varying. So this is 4 length 0 to 3. So we vary this k and n 0 to 3 like here. So n is 4 here. So we vary that. The equation of DST becomes x of n into n is varying from 0 to 3, and k also can be varied from 0 to 3 to obtain these coefficients, that is transformed coefficients, k pi into k plus 1, n into n plus 1 by 5. So now this is the kernel matrix, so can get the kernel matrix for it. So for first value DST S1, that is going to be A, where k equal to 0 and n equal to 0. So we get here from this 0 0, this is pi by 5, so root 2 by 5 into sine 5. So that's what root 2 by 5, the factor into sine pi by 5 for 0 0, k and n 0 0, and then we get the value of 2 pi 1 1, 2 pi by 5. So it's approximately 0.37 and 0.6 values. So if you keep calculating it 0 0 0 1 1 0 1 so on, so we get the values of A, B, B and A, and B. This is the kernel matrix now for this for n equal to 4. So which has A, B, B, A, B, A minus B and so on. So this A and B values are this. So now we have this DST matrix and then multiply this with X. So like what we do in the DFT, 1D DFT, we have this two-dimensional factor matrix and then multiply the sequence and get it to the transform domain. So that this S is now A value and B, and this is minus A and minus B, and similarly the other one here it is B and A and so on. So all A and B values are filled here. That's 0.371 and what we had computed. So from that Sx, that is transformed coefficients, this S matrix into X, the sequence, we can multiply one by one, that is going to be 4, 3, minus 1 and 6. These are the values of the X sequence. So if we multiply that for S0, we get 4.9205, and then S1, similarly if we compute the second row of S and the sequence, so it results in this value, and then S2, that is the third row, into X would give the value of 5.2715, and also S3, the sequence of the S third row, and then 0 1 2 3 in that row, it gives us the minus 3.1494. So 4 rows are there. S0 is first row, this is second, third and fourth rows, we got it minus 3.1495. So now make this as a vector which is giving the transformed domain coefficients 4.92 and 0.28, 0.27 and minus 0.314. So these are the coefficients of obtained through the DST transform, 1D DST transform for the signal sequence X, that is one dimensional, and the matrix or the kernel of the DST we obtained it for the n equal to 4 by 4. Now that's a 4-point DST. So can we consider this in the 2D DST, and that too in the separable form, because this DCT is separable, DFT is separable, and DST also DC is separable. So we use that in the 2D separable form. So that is row column wise decomposition. So in that way also this n cross n matrix X, that is X is the sequence signal what we have the 2D signal, and which is n cross n, and the 2D DST of it for will be, if you take the 2D DFT of X, the transformed coefficients are V. So V can be written as X into S transpose, as we have seen in the separable form of the DCT and DFT also. So 2D DFT, F and F, the two-dimensional factor matrices or the kernel matrices are getting multiplied with 1 and with the transpose. So this is unitary and real, and we have this S transpose is S we had seen. So the V can be easily obtained from knowing S. Multiplying this Sx into S, we get the transformed DST. This is for the case of 2D, that is separable form. So now we have this inverse DCT. From this X can be obtained S into V into S, or this is S dagger B S conjugate. So this is a conjugate transpose, and we have so because of S, this S asterisk represents here as S, that is equal to S transpose, and that is equal to S inverse. So these is symmetrical, and the orthonormal properties results in S. So X equal to SBS simply. So we can get back the X from the transformed coefficients, that is V. So this is similar to the case of the separable form. First row column decomposition. First do it for the row and then do the column wise DST. Similar, or column wise DFT first and then do it for the row wise DST. So both the ways it can be done. So that's it's just clubbed into one operation where S into X into S transpose. So that's how the transform coefficients have been applied. This is applicable. This we are getting because of the separability concept, that DST is separable. So from this it provides the, as we have seen, that it is very much used in the images as well. So it's an excellent energy compaction properties it possesses. So we'll take an example of this X 2D sequence and apply this 2D DST for it. So if we have this X equal to 2, 3, 4, 2. So when we have these X giving in the matrix form, that is 2D, we take the 2D DST of it, that n is 2, n cross n is coming to be 2 cross 2, right? So in this matrix, what is the DST matrix for S for this n equal to 2? That is a kernel. We have to first find the kernel of this. So for finding the kernel, S k comma n, root 2 by 3, that is n plus 1, 3 plus 1 sin pi k plus 1 into n plus 1 by 3, that is n plus 1 here, 2 plus 1 3. So if you vary k and n between 0 and 1, so S of 0 comma 0, S of 0 comma 1, and then S of 1 comma 0, and then S of 1 comma 1. So we can get all of this. So 0 comma 0, compute that, 0 0 here, it is going to be pi by 3 sin pi by 3 root 2 by 3, so which gives to be 1 by root 2. And then find the S of 0 comma 1, that is root 2 by 3. Here this is going to be 0 and this is 1, so we get 2 pi by 3, which is 1 by into root 2 by 3, which is going to be 1 by root 2, the resultant. And similarly 1 0, k is 1 and n is 0, you can get also sin 2 by 3 again. Sin 1 comma 1, in this case k and 1 n are 1, so we again we substitute in this one, get it 1 by root 2. So S contains these 4 elements, which is the kernel. So 1 by root 2, 1 by root 2, 1 by root 2, and 1 minus 1 by root 2. So S becomes 1 by root 2, 1 by root 2, 1 by root 2, and minus 1 by root 2. This is the kernel for the 2D DST of 2 by 2. Okay, so now taking this S and multiply it by X and then by S. This is S transform anyway. S transform is having this, so equal to S. So we just get this, the transform coefficients here Sx. So S and X is 2 3. This is going to be 2 3 4 2 the values, and do the matrix multiplication. So we get 6 by root 2. And this row and 3 by 2, this gives 5 by root 2, and this row and 2 4 results in minus 2 by root 2, this row and 3 2 gives 1 by root 2. So the Sx, after getting the Sx, this one, and multiply again with S. So you should proceed in this order. I should not be changing the order here. Sx into S, so which is giving the S equal to again this is the kernel, 1 by root 2, 1 by root 2. So multiplying them, the each row here, and then each row here, and this row and this row. So getting their V as 11 by 2, 1 by 2, minus 1 by 2, and minus 3 by 2. So now from the transform coefficients, can we get the X back? Yes, it is possible to get the X back. Okay, and moreover, what is this V consisting of? Actually, what are the basis images for it? So basis image corresponding to KL is given outer product of kth column and the lth column of S. So S and this V, how are they related? Okay, so how can we get back this using the basis images? So that's how we are going to do that. The column of S are, so we have the S kernel we had, right, that is 1 by root 2, 1 by root 2 the first column, and the second column is 1 by root 2 minus 1 by root 2. So that's the column we had. So this and the basis 0 0. So how basis image, to get the basis image and basis image and V, we'll see that how they are related also. So B 0 0, here 0 S0 and its transpose. So the kernel, the column and its transpose, the row. So this will be 2 cross 1 and that will be 1 cross 2. So the transpose, we multiply it, we get 2 cross 2. That means 1 by root 2, 1 by root 2, this column, and 1 by root 2 and 1 by root 2, this row, multiply the 2. So we get here we have the 1 by 2 into 1 1 1. So that's what B00, the result of this multiplication gives the B00. So if you want the basis image of 0 1, let us take 0 1, the next one, and S0 and S1. So this is corresponding to first S0 and this is corresponding to S1. So for first column and the second column, there are the 0th one and the first one. So the one transpose, S0 and S1 transpose. So if you take S0, that is 1 by root 2 and 1 by root 2, and the S1 transpose, that is 1 by root 2 minus 1 by root 2. And its transpose. If you multiply them, we get this one. This is 1 by 2 here, minus 1 by 2, and so on. So we get the case of 1 1 1 minus 1 minus 1 1 by 2 0 1 here, 1 and minus 1, and this is 1 and this is minus 1. So that's how we get the 2 by 2 0 1. So similarly, B10, we have S1, this matrix, 1 by root 2 and 1 by root 2 minus, okay, and its S0 transpose, that is 1 by root 2 and 1 by root 2. If you multiply them, we get this 1 by 2 1 1 minus 1 and minus 1. So this is B10. So similarly, B11 can be obtained also, this one and its transpose. If you multiply that, we get one more basis image. So there are 4 basis images involved in the V, the transformed coefficients, transformed image what we got. So can we do that using can we get back this image using the basis images? Can we get back the original image? Yes, it is possible to get back the original image, that is having the B00011011. So we multiply this B00 with the coefficient what we got in V, first coefficient, and then add it with B01 and its V coefficient, and B10 and its V coefficient, B11 and its V coefficient. So then you can reconstruct that image X back from this. So it is possible to have the image and its transform, and from the inverse of it, we can from the transformed image we can get the original image back from transform coefficients. I mean, the transformed means there's a coefficient, from that we can get back the original image because it has an inverse transform, and moreover we use this as a 2D separable form. The separability concept has been applied. So because this transform is separable, DST and DCT and DFT, all of them, so we can use the separable form as in the easy manner to have just use the kernel of the 1D also. And in 2D cases, row wise and column wise decomposition, we get the factor matrix in the case of DFT, and the same thing is called as kernel, depends on the basis function for DCT and DST. So these DCT and DST has the energy compaction property and the separability concept. Also the we can even getting the basis images and get back the image from the coefficients what we got through the combinations. So we'll see them with an examples in the next lecture. Thank you.